So we continue. And at the end of yesterday, I told you that we measured the electric dipole moment of the neutron. And we find a tiny, tiny number. Well, theoretically, we expect it to be 10 order of magnitude bigger, which tells us that the theta angle of QCD is less than 10 to the minus 11. Some other CP angles in the Saturn model, the delta CP in the CKM matrix, is order 1. So now we need to understand how is this angle and this angle, they serve a very similar purpose, but like the numbers are so much different. Okay? So again, let's learn from the things that we know. And we'll start with a very classical pictures of how a neutron looks like. It's not how it actually looks like, but it helps us to understand this problem here that we're going to study. And then we'll maybe say a little bit more about the actual problem. Okay? So let me draw a neutron. And let's pretend, so the neutron is charge neutral, meaning it has one up quark and two down quark, right? So, this particle is up quark, it has charge 2/3, and this has a charge 1 minus 1/3. So when you combine them, you get charge neutral. So it doesn't have a monopole moment, right? So now let's put in these quarks inside the neutron. And generically, I can say I do something like this, okay? I have an up and two down, right? So if I draw it like this, does this thing have a dipole moment, electric dipole moment? It does, right? So the dipole moment in this direction go from the negative charge particle pointing to the positive charge particle, okay? So let's call this theta. And let's change theta, okay? So I can change theta from this picture, and let's say I go to a picture like this, okay? Where I have up in the middle, I have two down, okay? So now theta equals 0, right? Does this have a dipole moment? No, right? So because it's symmetric, and the dipole moment is 0, right? So this is my classical picture of a neutron. And of course, it's not really a neutron, but it allows us to compare to something else that we already know. What other things have structures like this? Maybe remove the circle. Let me remove the circle. What does it look like? It looks like a molecule, right? So and now let's look at the different molecules. The ones that we know a lot. The first thing, let's say water. I have one hydrogen, one oxygen, one hydrogen. I have CO2, right? Which look like this. This one has an electric dipole moment because this angle is not 180 degrees. This one does not because this angle is 180 degrees. It looks exactly like the right-hand picture and does not have electric dipole moment. Okay? So now the question of understanding why does my neutron not having an EDM maybe is related to understanding how does my molecule doesn't have an EDM, right? So for a molecule, we understand it a little bit better. And we can even approximate even more instead of like thinking of a molecule which has some things which is, well, like in a line, I can think of this thing, right? I can bend it. Let's say like if this part is at a charge positive, the end is charge negative. If I bend it, I get a electric dipole moment, right? If it is not bended, then it doesn't have an electric dipole moment. Okay, so the dipole moment here is proportional to theta. And like when we look at this thing, right, we understand that if we bend it, it's not the ground state. It wants to go back when I release it, right? It is bended only because I apply a force to make sure that it is bended. Otherwise, if one wants to relax to a position, it's true for CO2, right? If I take this oscillator, I want to bend it a little bit, it wants to go back. And that oscillation is a vibration oscillation of the molecule. The water too, right? If I want to force the angle to change, it doesn't want to change, and I want to go back. So what we are seeing here with both this and the molecules is now for all of these systems, theta is not only a variable, right? It's a dynamical field, and it wants to be at a specific position. So the two things we can see from the molecules, one, theta is not a constant. It's a field, right? And here, like I just mean a classical field. It doesn't have to be quantum. So things that Faraday told us exist, right? And secondly, theta is not only a field, but like theta has a potential, right? And it has a minimum. And the V theta has a minimum for CO2 at the theta equals 0, and for this at some theta critical value, right? I don't really remember what's the theta angle for water, but it doesn't really matter. There is a specific point the molecule wants to be in, which is the ground state. Okay, so this is what happens for my molecules. So now the third thing that we know from molecules is, as I said, if I bend the molecule wants to go back, right? So there is a mechanism for relaxing the theta from some initial value, which is not the critical value, to go back to its critical value, right? All three things are true for my molecules, no matter what the theta wants to be. Questions? Okay. Everyone is happy with molecules. Now let's go to the neutron, right? So similarly, I can think of the neutron problem like this. I can say, what if I promote this angle, which is basically related to theta QCD, right, to a dynamical field? If I promote this angle to a dynamical field, then it wants to relax to a value, and hopefully that value is 0. And that is basically the idea behind the QCD axion. So the QCD axion, the idea is I turn this theta angle, right, theta QCD, into a field. And this field I'm calling A. And especially I will be writing theta equals A over F. So this is the pseudo-scalar field. So it's like a scalar field. So it has dimension 1. And then I need to introduce scale, which is Fa, the axion decay constant, to balance the dimensions. Okay? So of course, any angle has dimension 0. Okay? So, so I did my first step. And then I want to understand, the second thing I need to understand is now when I have this field, which value does it want to relax to? And what people can compute is basically the energy as a function of theta. And this is some complicated computation, but in the end, what people found is that it has a minimum at theta equals 0. Okay? So this is good. So what it means is that if I promote this angle to a field, then it wants to relax the theta angle to 0. It wants to relax the theta QCD to 0, which is why we didn't observe neutron dipole moment. Okay? And then we want to understand also the third question. Let's say, like in the early universe, I put in a theta QCD, which is at a random value, what is the mechanism that make this theta go to 0, right? There has to be a relaxing mechanism that turns this initial theta QCD to 0, right? And that will be some evolution of this axion field, and that's the thing that will allow us to finally see how this particle can be dark matter.
Theta QCD is where the minimum is. What is theta QCD? The minimum.
So theta QCD is like an angle that we put in, right, initially. And then we say like it's a field. And then we say like the field has some dynamics which makes this angle, right, that appears. So there's one thing that I erased, which is this is theta QCD times E Fermi, right, yesterday. So this is the term, the variable that appears in the measurement of EDM. That's what is theta QCD. And the axion is a field which relaxes this number to 0. Okay? Yeah.
Why this number needs to be relaxed?
Like if I start with an initial value, which is order 1, right? Generically, I start with order 1. If it is not relaxed, then I'm going to see an EDM of order Fermi instead of 10 to the minus 26 centimeter, right? So that's why we need to introduce this axion field to make sure that this initial angle, like after evolution, so after evolution, in the early universe goes to theta equals 0. Okay?
So is there a way we can know if this angle were bigger in the early universe, or it's just a guess?
Well, like we don't know if it is definitely bigger in the early universe, but just like when I'm forming a molecule, right? I put in a carbon and 2 oxygen. Initially, it's going to be in a random configuration, right? And it forms a molecule, and it vibrates until the point like it releases all its vibrational energy and looks like a ground state. Here it's the same. Initially, I would expect this angle to be somewhat random, and then like after some evolution, it becomes 0. Other questions? Okay. So now let's see how does this angle relax to 0, right? So let's come back to this molecule picture, right? As we said, in the molecule picture, this angle is like is relaxed by vibration, right? So it's like a vibrational mode. So here it's actually similar, and for all vibrational mode, right, or any mode, we can treat it as a harmonic oscillator, right? Like that's basically what it is. So let's write down an oscillator equation. So which is actually the equation of motion, which describes this angle as well. So the equation of motion we can write down is some A double dot, right, plus some friction term times A dot, right, plus some derivative of a potential. And I'm interested in small changes of this A field. So I'm expanding around the minimum. And around a minimum of a potential, I always have a quadratic term, right? So this, I can approximate it to be ma squared times A, right? So the potential has dimension 4, and one derivative has dimension 3. So this is a term that I will insert here. So yeah, just if I write it properly, then at the linear order perturbation, this is what I get for my equation, right? I have a mass term, which tells me how fast my oscillator is oscillating, and then like I put a friction term, which is this guy, right? So here, as you can see, I ignored. So this is the field in 4-dimensional space, right? So in principle, it also has spatial variations. And for all practical purposes, the spatial variation of the axion field in the early universe is very small. So I just forget about it and look at the simpler picture. So this is what we get, a harmonic oscillator equation. Okay? So what's more is I can actually also tell you what is this gamma, what's the friction. So the friction is actually coming from the Hubble expansion of the universe. So to exactly get that, like you need to write down the action and expand. But here, what you will be able to see is that the friction is provided by Hubble expansion, which is like a friction that makes sure that the scalar field won't move in the early universe. And if you remember from our FRW slides, we'll have like this Hubble scale is basically 1/2t, right? So it's a quantity which decreases as time evolves. Okay, so now with this, I get my equation of motion, and I know exactly what each term is. Now we can study its behavior, right? So first, let's look at like a very early time, right? So at very early time, Hubble is very big. M is something that's constant, so it's kind of small. So you can always go to some like a very, very early time such that this term dominates. And in this case, so t like early time, I have the first two terms are the most important, right? Right. So, and I know what the solution of this is, right? A equals a constant is a solution. And this is over-damped oscillator, right? So the amplitude of the oscillation doesn't change to start with. So at early time, when Hubble is much, much bigger than MA, my A of t is a constant, right? So that's, and it's a constant, so I can track it all the way to the beginning, so it's all equal to AI. So that's how it looks like in the very beginning, okay? So at some point, the Hubble continued to decrease, and it become comparable to MA, right? So now I don't have like I cannot like ignore this term. I have all three terms important. And now like I have a real oscillator equation. So this thing is going to oscillate, but it is a damped oscillator, so the amplitude goes down, right? So this is basically how I would expect this behavior to be as Hubble becomes comparable to MA. Of course, Hubble will continue to decrease afterwards. And after some time, basically, this term becomes less and less important compared to this term. So now, instead of having a damped oscillator, I just have a harmonic oscillator. And this thing is just continue to oscillate. OK? So that's basically the behavior of the axion field in the early universe. It started as a constant with initial misalignment field value. It oscillates, the amplitude goes down as a function of time. Okay? Good with this picture?
Professor, isn't there an exponential solution to the differential equation as well?
Exponential. Yeah, so like, actually, I think like this is probably like a minus sign here. Yeah, so like, so this is actually probably a minus sign here. So like, if you have a friction, you can either have like a constant solution, and I think like you can potentially have a growing solution. But like, I don't want like the growing solution, right? The amplitude cannot be continue to grow. Like, it has to get some energy from somewhere if it wants to do that. And that's not something I want. Right. OK? All right, so this is basically my axion evolution in the early universe. Now let's, like in the case of the WIMPs, I need to know what's the energy density I get, right? So up to this point, what I have is basically some A initial, right? So for my scalar field, the energy density is some dA squared. So this is equal to ma squared times at squared. So initially, I have some constant amplitude, and this rho is constant. OK? So this is very early on. So, and this is equal to ma squared ai squared, right? Rho ai, initial. So this density starts to decrease when this field starts to oscillate at the time when Hubble is comparable to ma, right? So from this condition, I know that what is the like other energy density in the universe, right? Because the universe energy density is equal to Hubble squared and Planck squared. And this is basically at that time ma squared and Planck squared, right? So this is also known as the T universe to the 4 at that time. It's radiation. So as we were using yesterday, right? The thing that stays constant is the number density of the particle over the number density of photon, right? So once like this particle starts behaving like matter, this ratio has to stay fixed, right? So again, this quantity is basically my rho initial over ma, right? The mass of the particle. If I take the energy density over the mass, I get a number density for a non-reactive particle. So this is ma squared ai squared. And the number density of gamma is t cubed, right? So I get ma to the 3/2 and Planck to the 3/2, OK? This is a quantity which stays a constant throughout. And now we go to matter radiation equality, right? So at T equals T equality, my energy density of axion over energy density of gamma is basically the energy of the axion over the energy of the photon at that time, right, times the number density ratio. Sorry. Square ma 3/2 and Planck 3/2. OK? Everybody good this step? OK, so my initial axion value, as I said, the theta has to be order 1. So AI is equal to Fa, the decay constant there, right, times theta I. Right? And theta I is order 1 number. Let's just approximate it to be 1. Gone. OK? So now what I get is ma to the 1/2 Fa to the squared over T equality and Planck 3/2, right? So up to this point, I reduce my density ratio to 2 parameters. It depends on the mass of the axion and the axion decay constant. So this is not great because it tells me like somehow like there is a relationship like these 2 parameters can satisfy, but like I don't know what is ma and what is Fa that will give me dark matter, right? So I need another relation. And the other relation we need comes from the fact that the axion, so the QCD axion especially, gets its mass from a potential that I know. And that potential is the QCD potential. And naively, I would expect the strength of the potential, right? This V of A. Where is V of A? So the strength of V of A, like which is equal to ma squared A squared. When I go to like its top, right, like the potential energy density in the whole barrier would be equal to where this potential comes from, which is roughly the QCD scale to the 4. All right, that's the physics that generates this axion potential. So the axion potential energy height has to be comparable to lambda QCD to the 4. So now I can substitute MA or FA into this equation using this relation. And this is what, so let's say like I put FA in there. Then this is equal to lambda QCD to the 4 over T equality and Planck 3/2 MA 3/2. Okay? And that has to be equal to 1, right? Good. So I know what this number is. I know what this number is. I know what this number is. It tells me what is the axion mass that will give me a dark matter. Okay? You can work out the numbers. Here I will just give you the answer. And what I'm getting is going to be MA, which is order 10 to the minus 5 eV. Okay? So it's a very small number. The particle is quite light. Its wavelength, if I want the Compton wavelength, which is 1 over m, what I'm getting is roughly a meter. Okay? It's a very, very light particle. And as a result, you know that this particle, I must have a lot of this particle, right? Compared to the Wimp, which is very heavy, it's TeV, which is 17 order magnitude heavier than this particle. In that case, I get very little particle per centimeter cubed. Here, if I'm talking about a particle which is 17 order magnitude lighter, then within every centimeter cubed, I would have a lot of particles of these axions. Yeah.
We started with this model for the quarks inside the neutron, and then we got dark matter particles.
Yeah.
What happened to the neutron that we began with?
So, so here, like, I will get to that, but like, okay, so I can tell you a quick answer. So here, like, what I'm doing is the third step, right? I'm saying, how does the QC axion angle relax to towards 0, right? And the evolution that allows this theta angle to go to 0 is basically this oscillation pattern, right? So what happens in the end is I'm getting like a really, really tiny theta angle here. Just like in the case of like a vibration of like molecules, eventually I get to a very, very small theta angle. Okay? So we'll be able to see like what's the theta angle like in a little bit. Okay? But before doing that, let's first compute what's the number density. Okay? So the number density is equal to the energy density over mass. And the dark matter energy density is roughly GeV over centimeter cubed. It's like 0.4 of that, but it doesn't really matter. And if I like over MA, which is 10 to the minus 5 eV, this is 10 to the 9 over 10 to the 5. So I get 10 to the 14 over centimeter cubed. Right? So now like the number density is huge. Every centimeter cube, I have 10 to the 14 of them. Okay? And the wavelength, as I said, is a meter, right? So basically, like within a Compton wavelength, the actual like more important thing is the Dipole wavelength. But like within a Compton wavelength, I get 10 to the 20 of these particles. So to describe the behavior of these particles, I cannot use particle anymore, right? I should be using waves. Okay, is it clear? Good. So yeah, so the last thing that I want to compute is after all of these oscillation, like what is the theta angle that I get in the end, right? Yeah.
So how can such a light particle be part of a cold dark matter? Isn't it supposed to be relativistic?
I will tell you, yes. Just hold your question for a little bit, okay? So first, that question first, okay? So theta t towards the very end can be computed from basically, so yeah, let me So I want to compute theta t, right? So there are two things. I have rho dark matter, right? As I said, is GeV over centimeter cubed. And the potential size is a lambda QCD to the 4, which is roughly like a GeV to the 4, right? So theta t is squared is equal to ma theta t squared over, right? I basically multiply both sides. I multiply like this thing by 1, right? So the top is the dark matter density today, right? It's equal to ma squared times a squared, while the bottom is the QCD energy density. So this is basically GeV over centimeter cubed over GeV to the 4, right? And you can work it out. This number is roughly like 10 to the minus 40, okay? Which means theta angle today, I have relaxed it from something that is order 1 to something that is 10 to the minus 20, okay? So that's how you see that I have fulfilled my promise to use a dynamical field through the early universe evolution to relax the theta QCD angle to 0, right? Right now, we can only measure to 10 to the minus 11. Of course, this is not exactly 0, but for all experimental purposes, it's 0. And again, we cannot never measure 0, so this is good enough. Okay? Good. So now, returning to the question, like, why does this particle, can this particle be dark matter, right? Earlier, so when we do WIMPs, it's easy to understand because this particle is very heavy, right? And the temperature is very cold in the galaxy, so the velocity of the particle is light, right? So here, naively, I would say, you are telling me that the mass is this, right? My TCMB is 10 to the minus 4 eV. So that temperature is bigger than this mass. How can this be dark matter? Well, the reason is, as you can see from like all of this derivation, right? The axion has never been symbolized with the standard model. It starts with the initial angle. It starts to oscillate, right? All of this oscillation is it's doing on its own. As the universe expands, it's just oscillating. So it's never like really in thermal contact with the standard model. So the temperature of the dark matter doesn't have to be the same. In this case, it's not really the same as the temperature of the standard model. The standard model temperature of the CMB photons is 10 to the minus 4 eV. For these things, the temperature is 0. This is not a thermal system. It has never thermalized with standard model. So even if it is very, very light, it can still be dark matter because the kinetic energy is 0. Does that answer your question?
Yeah, I mean, it's very crazy.
It's not very crazy. Well, like a lot of things are not thermalized, right? Our motion is not totally thermalized with the gas around us. So there's no reason for like some early universe dark matter particles to be thermalized with us. But like despite there being no thermalization, this is an absolutely fine production mechanism. Okay? So here, what we, and to show that, there's one last number I want to compute. So here, like I have MA, which is 10 to the minus 5 eV, right? I know like MA times FA is order lambda QCD squared. So you can ask, what is FA? So this is roughly like a GeV squared. Actually, it's more like a 0.1 GeV squared over 10 to the minus 5 eV. And if you work it out, it gives you 10 to the 12 GeV. Okay? So the axion decay constant is an enormous scale. It is a scale that is 8, 9 order magnitude bigger than the weak scale. And that's like one of the reasons why this particles couple so weakly that in the early universe, it would have no chance of ever thermalizing with the standard model. Okay?
Yes, that's 10 to the 12.
12. Okay. Questions? Okay. So that's basically most of the QCD axion. So if you have actually like worked it out before, like you will realize that I have cheated a little bit, because the QCD axion actually doesn't have exactly this thermal history. This would be an axion whose mass has always been on throughout the age of early universe. In reality, as I said, the QCD axion gets a mass from the QCD effects, right? And this potential only turns on when confinement happens. So the mass only turns on when the universe temperature is 1 GeV. And if you go back and work out like when, what temperature does this particle start to, we'll have like MA equals Hubble, you will realize that this estimate would assume that the particle mass is already on at the time when Hubble is like when the temperature of the universe is much more than 1 GeV. So in reality, what happens is that the mass of the axion as compared to Hubble, so I'm plotting Hubble with the white and using yellow for the MA. So my Hubble is decreasing as a function of time, and MA is increasing like this and become a constant, okay? And the time this happens is when temperature of the universe is roughly 1 GeV. Okay, so in reality, you need to, the time when like MA equals Hubble is a little bit different from what I estimated. And there's also a WKB approximation to do to get exactly correct axion density. So all of these dynamics is in one of the reading materials I attached, like a TASI lecture. If you are interested, you can look it up and maybe work out for yourself. But that will require some understanding of field theory. So for this class, this is actually a good enough estimate. It gives you the qualitative picture of a very light particle, and which is never in thermal equilibrium, and it is, as a result, cold, and cold enough to be dark matter. Okay? So that's all I want to say about a QCD axion. Questions for now before we go to experiment? Okay.
Yeah, one obvious question for me is which model do you think it has the most chance of actually being dark matter?
So I would say like the most well-motivated ones are QCD axion and the Wimp. Of course, there are other dark matter models, and there are as many dark matter models as a particle physicist, almost. And but like I would say, like if you ask everybody, like these are the two most well-motivated, they are most likely to be true. But again, like searching for dark matter is a hard business, and we don't know like if one of the two is going to be the dark matter. The chances are quite low, and maybe someone else will be able to find a much better model. Maybe you will find a much better model, and then we'll be interested in looking at the phenomenology of that too. So we look until we find it. If we didn't, then we look harder. Okay? Everybody happy? So now let's see how we look. So in the next, how long? Half an hour. And tomorrow's lecture, I will be telling you about how to design experiment and how to think like an experimentalist. As I was talking to some of you yesterday and over the week, none of you have been, well, most of you probably have never been an experimentalist. It's interesting to be an experimentalist. And if you want, you can try. Yeah.
I have a question. In the procedure that you show us,
Yeah, it has to be a boson, right? Because it has an occupation number of 10 to the 20. It has to be a boson, right? A fermion, you can only have an occupation number of 1, right? So all of these light dark matter candidates has to be a boson. More questions? Okay. So now we answered like these 2 questions for both the Wimp and axions. Let's go to question number 4. How to be an experimentalist? Okay. So to start with, let's think about some of the experiments that I'm sure like most of you already know, and how we interpreted like these experiments if we were going to be a dark matter theorist or experimentalist, or maybe both. Okay. So so the question we have at hand to look for dark matter, we don't know what it is. We know it's around here. It's like a fluid. It has a lot of particles, maybe a little bit more in the case of axions, a little bit less like in the case of the Wimps, right? So we are looking for this unknown substance in the fluid around us, and we try to see like what type of detectors would be better at looking at these new particles, right? So we have done that, and we have done that 100 years ago, more importantly, when we were first discovering things like molecules, atoms, as a part of a fluid, right? And that experiment, which is the first experiment I want to be talking about, is Brownian motion. Okay? So how many of you have heard of Brownian motion? Good. Okay. Brownian motion. It's actually like to me like one of the most amazing experiments. It is so simple, but it tells us something like very, very deep, right? So what do we have in Brownian motion? I have a pot of water or something liquid, right? And I spray, spray some pollen inside this pot of water, right? What happens is that, as we know now, the fluid is made of water molecules, let's say, right? And these molecules are moving around, having their own thermal motion. So they will move around, they will hit the pollen, push it a little bit, give it a little bit of momentum, so the pollen move a little bit. The pollen hits like another water molecule, go here, right? Go some random trajectory. And what people observe is that the distance it travels is proportional to the square root of time, right? So as you guys all know, famously Einstein solved this problem, postulating that the liquid has a lot of little molecules inside, and they have their own thermal motion hitting these things, causing the pollens to go random motion, and that's random motion or Brownian motion, and that's why the distance goes square root of t. And this experiment, despite it being very, very simple, tells us that the fluid, which is the liquid, is made out of small molecules which are moving around very fast. Right? So that's basically, that same idea is used to look for dark matter. And it is pretty much the only, well, the most important idea which is used to look for Wimps. And that's the idea of collisions, right? So the idea is dark matter is a fluid. It has its motion. It is moving around. And we, as detectors, is sitting inside this dark matter fluid. It hits us. It hits some molecules or some atoms or even some nucleus inside a detector, causing this nucleus, electrons, and everything to move around a little bit, depositing some energy, and we try to read out that energy, right? So in that case, just like in Brownian motion, we are trying to use some tiny detector, or like some very precise detector, which is a pollen, right, to look for the underlying motion of the fluid, which is the dark matter, right? So deposit some energy and cause motion of some detector. So here, like, I don't necessarily mean like the detector itself is moving like in its central mass, but some component of the detector might be moving, right? And we'll see that, of course, not everything can be used to look for Brownian motion here, right? We know. Like if you put me in a bathtub, like I'm not going to experience Brownian motion. I'm too heavy, right? So that means, as an experimentalist, you need to find the right thing to be put in the dark matter fluid and see how the energy gets deposited from the dark matter fluid to your detector, right? So that's important. So, but that's collision, and collision is very important. And the scattering, or like scattering, is one of the main ways we are trying to look for dark matter. Okay? So, number 2, let's get even simpler. A car. Okay? A car is a detector. Okay? And let me explain you how it detects particles. So, you probably, well, you are from, many of you probably from warm regions. I'm sometimes from a cold region in Canada. But if you are in the summer, you go to your car, you open the door, you get inside. It's super hot inside, right? And the reason it gets so hot inside in the car is because the car has been getting energy as you are away from the sunlight, right? So the sunlight shines on the car, causes some vibration of the molecules or whatever inside your car, and deposit heat inside, like on the exterior of the car, which gets inside, which makes it hot and bearable, right? So what's the concept here? The concept here is absorption. So that's the second type of way like energy can be deposited from the dark matter to us, right? If dark matter is some wave, like light rays, it can come to your detector, like oscillate the molecules of atoms inside, deposit some energy, and this energy you look for, right? So that's absorption. And it is the idea behind a lot of the particle detectors. May I finish? Okay. So, from very, very simple ones like the car, and two things called a calorimeter. I don't know if you remember. Two things that is super, super complicated called transition edge sensor. And those detectors basically involves me putting a superconductor on its, exactly at the TC, such that like if I heat it up a little bit, it will not be superconducting, and that's how I can see a signal. So for these detectors, we can measure heat deposition or energy deposition that is less than EV now. So, but like all of these very, very sensitive detectors, the idea behind it is absorption. We are sending some particle in, and it turns into heat, and that's the heat is what we are trying to measure. So, your question.
So this mechanism of absorption can't be electromagnetic, right?
So it, well, like of course, dark matter is not charged, right? So it's not purely electromagnetic, but like there are other forces, like our electron can be coupled to other waves. For example, the Axion wave will come in, oscillate the electron or nucleon, like through its scattering with it, and deposit some heat. We'll see that.
What's the scale of, another question, what is the scale of the detectors, the scale of energy? I didn't hear.
So what's the scale of the energy that's deposited? Well, I would say like anywhere from like 0.1 EV, that's the lowest we can look for, like with a calorimeter, all the way to like maybe KeV, GeV, like those energies.
To find the next
Yes, so we'll get to axions. We'll show you how it works because I have yet one more thing to tell you. Okay.
Related to absorption, how can we isolate the dark matter? Because why cannot we like relate that energy absorption with anything else? How
Good. You are already touching on the next concept I will be telling you. So the question is, how can I tell like if some signal is caused by dark matter? Well, so the way that you do it is you make sure that there's no background. And that is pretty much the hardest part about building experiment. Okay? All right, so absorption. The third thing that I will be telling you about is something that some of you might be holding now, and that's a cell phone. Okay? The cell phone is a different type of detector. So, and here, like I'm really talking about the old school cell phone, right? Like your grandma's telephone. So what does it do, right? So it when you speak into the thing, it turns sound waves, right, into some vibration, which eventually turns into electromagnetic waves. And when you receive a call, the electromagnetic information is turned into sound, which your ear, which is the detector, can receive, right? So here, the cell phone is a very important device, and it also gives you an interesting concept, which is conversion, right? So maybe we can cook up some device to turn, instead of sound waves, dark matter waves into electromagnetic waves, right? Or phonon waves, or spin waves, or any kind of waves that we can look for. And then after I turn the dark matter wave into these waves, I look for the existence of these waves, which somewhat match with the property of the dark matter. Okay? So the absorption and conversion are somewhat similar, right? So both cases, both of these are more likely to be used for particles that are behaving like waves. You can absorb them or convert them into something else. The difference here is that in the case of the absorption, I'm taking one quanta, right, which has some energy, omega or E, and turn into heat, which usually is a lot of quanta with much lower energies. Well, in the case of conversion, what we are trying to do is we are trying to turn a wave with energy omega into another wave with the same energy. So tomorrow I will show you an example how this can be done. Yeah?
Can there be any way to go the other way around, like from some other kind of wave that we know how to put this into?
Yes. So the question is, can I go other way around? Can I start with some electromagnetic wave and turn into dark matter? Yes, you can. And there are actually experiments that does it. Actually, there are experiments which turns electromagnetic wave into a dark matter wave and convert it even back to the electromagnetic wave. Okay? So, and this experiment is called light through wall. Okay? So what you are doing is you put two walls here. You send a laser at the wall. The wall blocks the laser. The photon cannot get through, but dark matter particles can get through. And then on the other side, you try to see if you have a signal, right? So if it is only photon waves, it cannot go through at all. If it can convert into dark matter wave and convert it back, then you will see a signal on the other side. And these experiments exist. It's called light through wall, and they are used to look for axions as well. But I'm not going to go into details about these. So there are many ways I can convert waves from one to the other, and we'll see one example only tomorrow. Okay? All right. So that's all for signal. So what I said, and I summarize here, is there are a couple of signals that we can get from dark matter. We can get it from collisions or scattering. We can get it from absorption. And we can get it from conversion, right? So all of the three are based on examples that you already know. So there's nothing that can prevent you from designing your own dark matter experiment, right? So that's all good. And actually, that's the first thing that you figure out when you are trying to design an experiment. But then you go to the experimentalist. You say, like, oh, I have this great idea. I'm doing this conversion. I'm turning dark matter into photons. And blah, 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 blah. And the experimentalist will look at you like politely for a while. And then he will say, OK. So what is about the background? Right? OK. So and in the next 15 minutes, I will be telling you about backgrounds. So to do that, maybe let's just think about this piece of paper again, or maybe this piece of paper again. So this is my dark matter detector. Okay? I'm holding this paper out, and I say this is my dark matter detector. Right? It's possible. The question is there a signal?
Probably, but from other fields.
So the question is only like, is there a signal? Does it do conversion? Does it do collision? Does it do absorption? Is there a signal if there's dark matter? Let's say Wimp. Anyone? There should be, right? There are signals, right? So I'm holding this paper out. There are WIMPs going this way. There are WIMPs going that way, right? So they scatter with my paper, deposit some heat, right? Deposit some energy, kinetic energy of the wind. So this paper heats up a little bit, right? So, well, on the other hand, another thing, so we are, like the Earth is rotating, we are rotating around the sun, right? So this thing is not stationary with respect to the fluid of dark matter, right? So there might be more dark matter going this way, less dark matter going that way. So there's a pressure, right? So my thing can measure pressure as well. There are dark matter waves which might be coupled to acoustic waves, right? So it will cause this thing to vibrate a little bit, right? So there are signals. There are all kinds of signals which can be deposited onto my piece of paper, right? But is there a good dark matter detector? No, right? It's not. And the reason is not because I don't have a signal. I always have a signal. The problem is always the background. And so what are the backgrounds that this paper has? Well, basically, pretty much all the signals that it can detect, right? So what are the background? What is this background? Huh?
You're holding, you're transmitting heat to
Yes, OK. But like more importantly, my hand is not very steady, right?
yeah.
So it vibrates. So there are vibrational noise. Right? My hand vibrates, the thing vibrates. So even if the detector vibrates, it could be my hand, it could be dark matter, I don't know. Right? It's probably mostly like my hand. So this is a vibrational noise. It's a very important source of noise. And there is a close cousin which is called gravity noise. And these noise are what the LIGO people are struggling with when they are trying to detect gravitational wave. Right? What other noise does it have? As you said, my hand is at a temperature, right? So so my hand is transmitting heat into the paper, which heats it up, or maybe cools it down. So there's a thermal noise. And more importantly, well, it's easy for experimentalists to design something which holds it in pace without transmitting heat to it. But like there's something that that is hard to cut off, right? I am 35 degree, 37 degree body temperature. It's 300 Kelvin. It's much harder than the CMB. Right? I'm emitting a lot of radiation. And those radiation are also thermal noise. Right? So if I really want to look for an axion of 10 to the minus 5 eV, right, which is 0.1 Kelvin, I pretty much need to cool my system down to that temperature. Otherwise, you are not really measuring dark matter. You are measuring the fact that we are hot, right? And we transmit heat to the detector. And that's the thermal noise, right? It's another important noise. And there are many, many more. There are magnetic field noise. Right? So as we'll see tomorrow, if you are looking for axions, we need to put a giant, like a constant magnetic field. But what it does is that, apart from like providing a background where the axion can convert to photon, is that it itself, right, like the magnetic field itself is a photon. So if now like my detector is not perfectly like built, then there are magnetic field lines which can leak into the detector. So I have leakage, and these leakage will be registered as signal. And now I have magnetic field noise, right? I have all kinds of spin noise, right? I have short noise. So the spin noise is similar to the B field noise. The short noise is basically like I'm only measuring the system so much time, right? Like I'm not like measuring like a system like an infinite amount of time. So like there are statistical fluctuations and quantum fluctuations, and as a result, I might have short noise, right? Like my detector is probably connected to some electronics. So the electronics also have noise, right? And most important, famously, most of the dark matter detectors we have, well, especially the very sensitive low energy ones, have a noise at 60 hertz, right? No, what is 60 hertz? It's coming from the, your energy source, right? Your electricity is oscillating at the 60 hertz. So if you have a detector which is connected to all these electronics, then you have an electronic noise which corresponds to oscillations at 60 hertz. So all of these noises, backgrounds, are important. And when you design an experiment, this is the first thing that you think about. How can I make sure that none of the noise is going to kill my signal, right? Overwhelm my signal, so I won't be able to look for, even if the dark matter is doing something to the detector. And I'm not going to go into how to, reduce all of this background. In the case of the examples I will be giving you tomorrow, which look for dark photon and axions, we'll talk about some of this noise. But like when you, in the future, design your experiment, right? These are the things that can stop you, right? If you fail to control your noise, then your experimental colleagues, they will look at you and will like, okay, you're not a crackpot, but very close to that. Okay. All right. So that's basically all the noise that we have. And lastly, let me go into a little bit more about WIMPs. So, so here, like what I will be telling you about is how does we go from this picture of Brownian motion to really like a WIMP detector. Okay? So how to make a WIMP detector? Okay? So to do that, let's first, what first you need to understand is what type of energy does the WIMP deposit, right? Let's say we have a TeV energy particle. This particle has mass, and it has kinetic energy. But the mass energy you cannot extract because it's a conserved quantum number. The dark matter, like quantum dark matter number cannot change. All it can give you is its kinetic energy. Once it becomes stationary, there's no energy you can extract from the particle. because otherwise you need to destroy it, right? And you cannot. Yeah?
If the Wimp is absorbed, then you have all of its energy. Is it?
What? Sorry, what?
If it's absorbed.
Yeah, you cannot absorb it because the Wimp has a conserved quantum number, right? So like you cannot destroy a Wimp. Like I cannot take a proton and take all its energy out because the proton has a conserved quantum number, baryon number. I cannot destroy a proton, or at least we don't know how to do it yet.
That is only for the axion, the absorption.
Absorption is only for waves, like yeah, things without a conserved quantum number. Yeah. So. Yeah, so that's why, like, first, the only thing I can do is collisions, right? And the energy I get is mv squared, right? So v is 10 to the minus 3, so this is 10 to the minus 3. So the maximum amount of energy I can get is around mmv, okay? And it's close to that. So here, what do we need to worry about? I don't need to worry about vibration, right? The vibration has very low frequency, very low energy. Thermal, not so much. Even if I'm like 1 eV, like temperature, like I'm not going to like emit something which is MEV, right? Well, like you need to worry a little bit, but like not so much. These, maybe not, right? These electronics maybe, okay? So this maybe, but also. One thing that I forgot to write down is cosmic rays and radioactivity. So these two are what I need to worry about for a Wimp, right? Because if I have a radioactive decay, I get energies that is ordered like 1 to 10 MeV, right? So they look similar to the energy that I'm depositing with the dark matter particle. So I need to worry about radioactivity, okay? So that's why. Can I use this as a detector? No, right? So this is not good. So what is good, right? Okay, so what type of material should I use to look for Wimp? So, okay, so yeah, maybe also chemical. So, in order to understand like what type of material like I should be using to look for a Wimp, let's see how does Wimp deposit energy, right? So of course, like when it deposits this much energy, it doesn't really destroy the nucleus, but probably your like atom is not like doing very well. Like when I give it MeV energy, right? The binding energy of hydrogen is 10 eV. So if I deposit like MeV energy to like an atom, I shouldn't be treating like the electrons as bound particles anymore. Right? So what I'm scattering here, as a result, is some dark matter particle which comes in, right? And it is hitting my atom. But more importantly, it is not really hitting the whole atom. It's really hitting the nucleus, right? It's not like interacting with my individual nucleon yet, because their binding energy is much more than this MeV energy, right? So in order to understand how does my dark matter interact with my detectors, my little polons, the little polons I will be actually using is not atoms, but I should be considering nucleus, right? So now I have a dark matter particle, which is a TeV, and I hit a nucleus, which is, let's say, like of some atomic number A, right? And the mass of the particle is basically A times GeV, maybe a factor of 2 or whatever, right? So what does it tell me about A? Does A want to be big or small? Small. It wants to be, so like what's the energy that's deposited in this case? How should I understand like the scattering? Which one is heavier?
Dark matter.
Dark matter is heavier, okay? So instead of thinking the dark matter hitting the nucleus, right? what is really happening is my nucleus coming in and getting reflected, right? So because like this one is lighter, so when I do the scattering, the energy that can be deposited is proportional to the reduced mass, not to the dark matter mass. Okay? And the reduced mass, when like A is less than 1,000 in this case, is always going to be roughly the nuclear mass. So the energy, so here like I cheated a little bit and I lied. Instead of MeV, the energy that I can actually deposit is basically A times GeV times velocity squared. So it's equal to A times KeV. Right? Good. So now, which A do I want? I want more energy. As a result, I want an A that is as big as I can. Right? I certainly don't want this fluid to be like very chemically reactive. Right? So, so then like my choices are basically helium. Sorry, like I actually don't. Kr, I think. I forgot what's the number, but like on all of these things, right? I want something that is chemically inert, and I want something which is as heavy as possible, right? So should I choose this one, whatever it is? Do you remember? Actually, what's the element? I forgot. Huh? Yeah. Radon? Okay. I forgot what it is. Like you guys can look up like the chemical, like a table. But anyway, so it's something here. Like, should I choose this one? Why can I not choose this one? It's radioactive. Okay, so I don't want anything that's radioactive, right? Because that's my noise. So the best thing I'm left over with is xenon. And xenon is good. Xenon is very chemically inert. It doesn't have radioactivity. At least I can purify it. And I can get a lot of it, which is good. I don't want to pay a lot of money to build my detector, right? So that's why, from like actually very simple considerations, right? I want a heavy nucleus that's not radioactive, right? One because of the signal, one because of the background. That I limit myself to this single element, xenon, to be the detector for dark matter. And that's basically why people are mostly building xenon detectors for WIMPs. And you have probably heard about things maybe like xenon 1-ton, xenon n-ton, Lux, LZ, Panda X. All of these things are xenon detectors. And the reason everybody is using the same element is because it's the one that is most suitable to look for WIMPs. And this is the element. For WIMPs, it is the best Dipole, right? Okay. The idea is exactly the same as a Brownian motion. I have dark matter particle coming in, deposit energy to the xenon, and we look for it. And with signal and background considerations, I arrive at the element I want. So that's all I want to say today. So like we talked a little bit about how dark matter, like what type of dark matter experiments we can build based on collisions, absorptions, and conversions. We talked a little bit about the various backgrounds we can have, right? And how we choose the right element to build a WIMP detector. So tomorrow, I will show you 1 or 2 examples where we see how we build a detector to look for waves. So as you can see, like the choices for WIMP detector is kind of simple, right? That's it. For waves, it gets way more complicated because we can have all kinds of couplings. We can do conversions. We can do absorptions. And we'll see like how we build these detectors. There's more magic involved. Okay, that's it.
Very good.
Right on time.
Okay,
Yeah.
I can run too.
So my question is, I was thinking during your presentation the following. I have seen a lot of people saying, oh, the neutrino fog as we get to lighter mass range. And I was thinking, neutrinos, I think maybe the noise that they may cause is related to vibration, maybe? I don't know. I don't know.
Oh, so like,
but
yeah.
how do experiments like, what are people thinking about how do we get like protected from these neutrinos like
Okay,
to
yeah. So the question is about a neutrino floor. So the one thing that I didn't mention when we talk about WIMPs is, actually I have some pictures, but I didn't bring my computer. So, basically like when we design WIMP detectors, when we use xenon, eventually like there is an irreducible noise. We are still like kind of far from it, which is called the neutrino floor. And those are basically like mostly like solar neutrinos, which comes in and hits the detector and deposits energy. Okay, so it gives you a signal that is very much similar to a dark matter scattering. But thanks to the fact that neutrinos also interact very, very weakly, we are not yet like facing this giant background that one cannot remove. So yeah, so the question is
what are people thinking how to approach this, like
yeah, so right. I think like people are trying and to design experiments which can distinguish neutrinos from WIMPs. And the way that that people are usually doing it is by using a detector which has directional information. Most of the neutrino is coming from the sun, where dark matter is coming from everywhere. So if you have a detector that will be able to tell you that this particle is not from the solar direction, then you know it's not neutrinos. Building these detectors are hard, and especially like for xenon detectors, we are talking about 1 ton or a few tons, like 4 tons, or like maybe some people are actually even talking about 50 tons of xenon, right? For these directional detectors, the materials are more expensive and it's harder to build them to these type of sizes. And so, yeah, it is not very, very easy to go below the neutrino floor. And that is also the reason why we are struggling at detecting the Higgs xenon, because that particle is famously like really, really close to that irreducible background.
Thank you.
Other questions? People are more interested in theory.
Don't be shy.
Okay.
So in the case of the collision, which kind of detector you will use to detect, well, the nucleus you're like returning, or I don't know how to say it, like
yeah.
after the collision?
So after the collision, right? So yeah, that's a good question. Actually, like there are many ways we can see the signal. So the collision basically means like my dark matter is coming in, knock the nucleus. So now it's like a, well, let's say like I have an atom and the nucleus is offset, right? So it wants to relax. So there are ionizations because of this process. And there are like photons, energy, heat that is deposited. So most of these detectors, the two things that people track are ionizations and photons coming out of like this collision. And we have models, or like even like a lot of simulations, which tells me like what happens when my like nucleus is like moved by a little bit by a dark matter particle. And then like we try to see if the signals that we see from the detector, so there's still some noise, and like whether the ionization and energy deposition matches what I expect from the cold dark matter particle like hitting my detector, instead of like some radioactive decay, which deposited the same amount of energy, but might have a different portion in different energy depositions. So that's how we use a Wimp detector. So there are xenons, and then there are also these semiconductor detectors, which do things somewhat similarly. But yeah, eventually you are going to use a detector to measure the energy that is deposited after this collision. Okay. More questions? Okay. Oh, okay. All right.
What's the situation with currently operating Wimp detectors? Are there any results that you find interesting?
Oh, so yeah, I will repeat. Yeah, actually, maybe it did work. Okay, so the question is like, can you summarize the situations of the current Wimp detectors? Are there results that are kind of interesting? Well, I would say like there are usually like some like once like in a while there are like detectors which report some like a signal. Usually like so in particle physics we have a very strict criteria when we consider a signal really discovery, right? Like we say, people might have heard about this thing called 5 sigma, meaning that even only when it's a statistical fluctuation that is more than 5 sigma away, like a Gaussian distribution, so it's very, very unlikely that we say like we have a discovery. But it happens a lot when we have some hint which is 2 sigma, and those things come in, people might think about it a little bit, but I wouldn't say like, I think like most of them are not like a conclusive. It's just like, okay, so this is a possibility, and we just wait for more data. At some point, maybe we'll get to 5 sigma, then we have a discovery. Otherwise, yeah, just it didn't matter like if I like the model, like they explain the signal or not. As long as it's not 5 sigma, like it's not, yeah. It's curious, it's not interesting. Yeah.
So if the dark matter is cold, shouldn't it become gravitationally attracted to each other and form like some kind of planets or star of dark matter?
Okay.
And this makes a kind of solar system scale of detection of this gravitational effect.
Okay. So the question is, if I have dark matter, like, and they interact gravitationally, why don't they cluster into some bound objects, like, let's say, like the star or whatever? So actually, to form stars, you don't only need gravity, right? So the Snell model particle forms stars, not only because of gravity, but it also has dissipation. So the gravitational force attracts these particles coming in. They will get faster, right? Naively, like it will be a very fluffy object. The reason it gets denser and denser, it becomes a star, is because it can emit photon and cool down. Right? If you cannot emit a photon and cool down, then you'll stay fluffy. So the dark matter, as far as we know, don't necessarily have a dissipation mechanism, so it cannot form like a very dense objects like stars.
But couldn't it emit like a dark photon?
Like in principle, yeah, like you can write down models where like dark matter has its own dissipation. So then like you can write models, you can say like, in my model, I do form dark stars, and people study that. And when you have this dark star formation, it usually means like your interaction has dissipation, and the interaction has to be relatively strong. So now you are like faced with the bullet cost bond, which tells you like the remaining dark matter, right? Not all the standard model particles in stars, most of them in gases in the galaxy. So what about these gases? Do they, like they don't satisfy the bullet cost bond? So it probably tells you like these dark stars are very unlikely to be formed, unless you have a way to turn all the dark matter into dark stars. We don't know how to do it for standard model. Maybe we can do it for dark matter, but unless you have a theory which can do that prediction, we don't know what to look for, right? Okay.
I don't know if you are going to say this on future, in the next lecture, but can you talk a little bit about the Derma experiment? And I don't know if I'm saying right the name of the experiment, but it says
Dalmar.
that, yeah.
Okay. Yeah, well, like I can say a little bit about Dalmar experiment. So Dalmar experiment is an experiment which use this instead of, well, like Dinang as your target. And it makes sense, somewhat makes sense because like this is also like a heavy nucleus, right? So it famously observed like some annual modulation. But there are many reasons we don't believe it. And I'm being recorded. I need to be careful. But so like yeah, but like so the problem with Dalmar is first like nobody can reproduce the result. They point to a cross section where we have done other experiments, and certainly it's not there. And then like the data analysis, as people have tried to reproduce their data analysis, is not done correctly. Because they are looking for annual modulation, and then they separate their data in 1 year sections, right? So you are introducing the signal into like from the analysis. And lastly, like they see a period which doesn't agree with the expectation from like a theory. So the idea, so like because of like the gravitational focusing effect coming from the sun, we can like and like all the stellar motion, like or planet motion in like the solar system, we can more or less predict like where like the dark matter density is the highest, on which day is the highest, and which day is the lowest, right? So so like that's basically the annual modulation, and yeah, people did the experiment. Like their experiment, the interpretation has a period with, like has a phase of like this oscillation, which is offset from what is predicted from theory. So, and that's the third reason like why people don't believe it, because yeah, you're not seeing like the right right annual modulation. Did I answer your question? Okay. Yeah. Right.
If it would be observed that strong interactions violate CP symmetry, and therefore there wouldn't be a strong CP problem, either QCD actions, the only remaining possibility for dark matter is to be Wimps?
Well, like there are other possibilities too. Well, like yeah, but like I would say, like in that case, then the Wimp is going to be the most well motivated. And I think like this experiments we are doing, we are putting most of our resources into Wimp for that reason. Most of the other dark matter detectors are like on the scales of like $1 million, well, like the $1 million, well, like most there are Wimp detectors. When you combine them, it can be like order like $100 million in total. So yeah, the resources we are putting into these detectors, of course, is correlated with how much we think like this dark matter candidate can be the real thing. Of course, there is a strong CP problem, and which is the reason why we are putting almost similar amount of resources now, like into axions. And yeah, and then like we are looking elsewhere. You know, like a lot of times in physics, the most important experiments coming somewhat unexpected. If you think about it, what are the most important experiments? Michelson and Morley, right? The CMB, which is like the basis of all of like our understanding of cosmology and a lot of particle physics, right? It's some radio people who cannot switch off their noise, right? And many other things, like we serious, like we say a lot of things, but like experimentalists might tell us like otherwise. And yeah, black body radiation, for example, right? All of these things come out unexpected at the time, and then like we interpret them, and then we find new ways to test the theory, and we move forward. So we are putting a lot of resources in the ones that are most well motivated, but like it's also important that we explore other options.
In those Wimp detectors, you were talking about the backgrounds, but what about those possible backgrounds that we don't know yet? For example, how do you can distinguish between the spiral neutrinos, for example, with the dark matter?
So like, well, spiral neutrino, like if we see it, then it's new physics. It's not necessarily like really a background, right? If it is dark matter, we are happy too. But like, yeah, there are, but like experimentally, like it's true. Like there are a lot of background. When you run the experiment, you don't know they exist. And then after you run the experiment, you are like, oh shoot, like there is something else I don't know, like my detector is not behaving, right? So that's why like I said, like it took us like 1 hour to have a good idea, or maybe like a week to have a good idea, work out the signal. It takes us 1 year to write a proposal which says, hey, experimentalists, like we thought about all your background. Please do it, right? And it usually takes many years for them actually to do it because there are a lot of unknown problems that can show up, and you just work out, like figure out ways that you can reduce all these backgrounds. And like when you work hard enough, right, like Penzias and Wilson with CMB, when you make sure that there's nothing that is leaking into your instrument, the only possibility is you have found something new. And that's how you do experiment. Yeah.
So how big or small, I don't know, can be these experiments, and also how expensive and difficult to build?
How deep?
Big. Big. Or
Big.
What's the size of this?
Oh, what's the size? Well, like the xenon detector is, I mean, like a few tons, right? So it's like a meter cubed, like it's like as big as this, like a room, or maybe even bigger. I mean, like most of the dark matter experiments are actually like this room size or bigger, but not because like the equipment that we are really using is like this big, but like there are a lot of electronics, and there are a lot of like components we need to make sure that we don't have background. And of course there are even bigger ones. There are super K. So super K is yeah, a giant tank of water. I actually don't remember like how much like a ton it is. It's like a kiloton, right? So it's like really huge, like a building. And yeah, and then like you go to LHC, which is, you know, kilometer size, LIGO, kilometer size. So yeah, so like a lot of these experiments are large, and many of them are expensive. The dark matter detectors, I think the most expensive is like tens of millions. Yeah. Is that good? Okay.